December 2022 Modeling and Simulation Community Meeting. Few things to go over today. We're very, very lucky to have two guest speakers today, if my system would cooperate. So I'll give a brief update of the field schedule for the 16B. And then following that, Ben Dyer from Geoenergy Swiss will present an update of some of the reprocessing and continued processing of the Stimulation 1 MEQ data. And then following that, Stuart Simmons will give us a detailed description of that teaser I gave last month for the composition of the flowback water from the first stimulation that we did back in April. So I'll launch right in. I don't have a whole lot to provide as far as an update for any field activities. Things are moving along, contracts are being let, plans are being finalized. Per our last management meeting, we are still looking at nominally the 1st of April to begin drilling. If Joe Moore, if you're on, want to provide a better info on that. I don't see you on the call, but so we're still moving ahead. We're on schedule. We are working on some of the final, we're working on some of the detailed planning now for things like flow test, flow confirmation. Once we get some of those things in an order or a state well enough to share, I will present that here to this community for feedback. I likely will be looking to do that in January or February. John McClellan and I are working on that pretty hard right now. We're going back and forth. It's a give and take to try to meet everyone's needs. So that's the last I have for any field update. And so without further ado, Ben, if you're ready, you can take over the screen. I'll go quiet. If you have questions, Ben, do you prefer to be interrupted as you go, or do you want me to filter and moderate for you?
You better filter and moderate, or I'll never get there.
All right, sir, we'll do that. So if you have questions, please type them in the chat, and I will interrupt as necessary if need be, or we'll hold them to the end. So thank you. Ben, it's all yours.
Okay. All right, have I got the screen? Can everybody see?
There you go. Perfect.
Yeah, perfect. All right. So good morning, ladies, gentlemen. And thanks for the introduction, Rob. So I'm going to present a quick update of the microseismic processing that we've been conducting of the stimulation in 16A in April. And there are quite a lot of open questions that I've heard over the last few months. So I'm going to go quickly from the beginning, actually. So here's a view of the site that we've seen lots of times, and really just to point out that we had 3 deep systems for monitoring. So there's in 7832B here, we have a deep 8-level 3-component geophone chain, and the same in 5832. And in 56, we had a 2-level chain. And as well as that, we had a 3-level 3-component fiber optic string on a trial basis in 78A. These are the tools that we were using, say the 2-level analog strings here. These are the deepest strings we had. They're in 56 and the maximum temperature 212 centigrade. And then the 2 8-level chains are here in 58 and 78B, sort of 180 and 175 centigrade. The 3-component prototype fiber optic tool is up here in 78A, so quite a lot shallower, but still in the granite. And in addition to that, we had the Silixa behind casing DAS systems in 78A and 78B. Now, there has been quite a lot of sort of comment on the sensors that were operational and the problems we had in the field. So I've just put together this table as a sort of summary of what was working and when. So the first 2 lines here, the 78A and B DAS, this is the Silixa system, and that was running throughout stages 1 to 3 and the VSP, so we didn't have any hiccups there. And also this system called BOSS, which is the 3-component fiber optic trial string, that was operating all the way through, but these are the relatively low temperature systems. In 58, we had the 8-level 3-component geophone chain, and that also operated through all 3 stages and the VSP. But we did have a small problem in stage 2 where it lost time synchronization, but this actually didn't cause us to lose any data. In 56, we had a lot of problems deploying in this well. We initially intended to deploy another 8-level string, but the primary string failed and also the backup. And so we reverted to the backup, which was the 2-level analog system. And that was working from stage 2 onwards, worked through stage 3 and failed just before the VSP. And then in 78B, we had a bit of bad luck here, really. We had two problems with the wire line. This is silly stuff, just cable head failures. And we didn't get that string running until stage 3, but then it ran for the BSP as well. So here's the fiber optic data, just to show you why we didn't use and what we did use and why. And so this is the so-called BOSS tool. This is the 3-component fiber optic sensor system. So this is at the bottom of 78A, just in the granite. And behind casing in 78A, we also have this DAS system of Silixa. And for the processing, we've used only the BOSS data because basically it's easier to pick. It's got about 2 to 5 times the signal to noise ratio of the DAS data. So though we've loaded the DAS data, we don't actually use it at the present time. And here is it's actually the largest event, and just to show you that the DAS data also sees the shear wave back here, the green lines. Can you actually see my mouse when I move it?
Yes.
Oh, you can. Okay, good. Okay, so that's all I want to say about the fiber optic data. We didn't use the DAS strings. So the first step in the processing then is to determine the P and the S velocity model. And we just use constant velocity since these sensors were all in the granite. And we use a sort of tomographic type technique to determine these two constant velocities. So we had 3 perforation shots, and essentially all we have to do is choose the velocities that fit the PIC times, which are the red pluses for the P wave and the blue pluses for the shear wave, to the model times, the times through the models. And so this is the perforation shot for stage 3. And you can see here we've got a good fit between the PIC and the model times for all of the strings, actually. For the shallow string, we also had to add some small station corrections because, of course, the velocity does vary a little bit as you go up shallow. And then the other thing we required for stage 1, when we only had the single 8-level string in operation in 58, was to determine the azimuth of the individual geophone groups. And this is because we had to use the azimuth of Hodderman ground data in order to locate the events for stage 1, which is the sort of red events over here. And so here's the 3-component data for the stage 3 perforation shot. The radial components are horizontal in this case because the hole is vertical, and they're shown in the red and the blue. And so here, each of these groups has been oriented so that the red is east and the blue is north. Obviously, we had 3 perforation shots. The azimuth of the geophone groups has got to be the same for all of these shots since it hasn't moved. The geophone chain has been clamped all the way through. And so what we see here is the 3 different symbols are the azimuth of the group derived from each of the 3 perforation shots. So this is group 6, and there's 3 different azimuths, but they're pretty close. So this is what we needed for the stage 1 processing. So the next thing to look at is the time synchronization problem, and this is how it appears. So this is what we see when we're doing real-time monitoring, is that we cease to get a good fit between our PICs, the red pluses and blue pluses, and the model times. And basically the trouble is because there's a time split between the groups, the different sensor group systems, and you can't find a location that fits anymore. But in this case, the slip was only a few tens of milliseconds, so the event appears in the same trigger window. So the event you're seeing here on 56 is the same event as you're seeing up here on 58. Right. Now, we know from using the GPS 1 second time signal that the traces in 56 and 78A are actually perfectly synchronized. And this was our method for testing and averting this problem. And so we could determine that the problem was with the 58 chain. And then in order to obtain the locations, all we have to do is treat the chain in 58 as if it's got a separate time 0. And so all we're really doing from finding the locations is fitting the move outs between these different groups that are on chain 58. And then we fit the relative arrival times of 56 and 78A. And this actually gives us a very good fit to the data and has negligible effect on the location. So here we've got a typical event from stage 1. I just show these typical events for each stage. And in this case, as say, we've only got the chain in 58 and the shallow sensor in 78A. So in this case, we have to locate the events using the hodograms. And this generally gives us a less accurate location than for the network. From stage 2, we have the chain in 58, but we also have the 2-level system in 56. And so now we can locate using triangulation, and it's a lot simpler. And again, in stage 3, we're locating using triangulation, but now we've got the chain in 78B as well. So these are our most reliable and accurate locations. And this is the largest event, where we can see very easily the PNS arrivals. And wouldn't life be a joy if they were all like this? Oops, gone too far. So here's a little plot just showing quickly the hydraulic data versus the seismic data. And the only real reason for putting this up is to show you that we were dealing with really very high trigger rates. Here in stage 1, we got 350 events per 10-minute interval. So it's around 2,000 triggers per hour that we have to process. In stage 2, there was a shut-in. This was conducted for about 30 minutes just to test the seismic response to shut-in. And we see, as you'd expect, that the trigger rate shown here by this sort of histogram falls off very quickly with the shut-in. But once we start injecting again, the trigger rate picks back up again, and it's continuing to increase. And I presume would have gone back up to the original level if we carried on injecting, but we started the down steps here before we got back to that pre-shut-in level. So now just have a quick look at the actual event locations. So these are all the locations we've derived to date. You'll see in all of these plots that follow now that the stage 1 events are shown as the red dots, stage 2 are green, and stage 3 are blue. And the perforation locations are the blue diamonds, so that's stage 1, 2, and 3. And the little green symbol there is the casing shoe. Now I think the next slide is going to be a bit tricky for me. There we go. So now I'm going to show the time sequence of the events. So this is stage 1, and what we see with stage 1 is the events start above and beneath the open hole. They don't actually start at the open hole, there are very few of them very close to it. And as time progresses, what we see is that the events grow upwards and downwards, but they also start to appear in this area further back up the well. And I don't think they're being connected here via the well or any leak along the casing or anything. I think the seismicity has grown up here and then it's stepped across to another feature here. And as this stage progresses, we see this seismicity growing back down towards the well and also upwards here. And you see this area at depth is filling in as well. And what we'll see next is the stage 2 events arriving. All right, so you see stage 1 has come down here towards the well, and then stage 2 are these green events that are actually starting infilling and where stage 1 finished off. And another interesting to say about this is that stage 2, there are no stage 2 events up here in the shallow zone. Right, so stage 2 is not connected to this region. That's all just stage 1. So now just let it run and you see stage 2 filling in here, and then you start to get another feature coming here and here. And stage 3, which is our most reliable and accurate locations, you can actually start to see sort of shapes in it. And stage 3 has also got a much more sort of, the plane is the wrong word, it's not a single, but it's multiple planes, it's a sort of finer structure. Okay. So another way of looking at the events then is to look at 100-foot depth slices. And so here's a vertical section. If we look first at the depth slice from 7,500 to 7,600 feet, that's shown here on the right. And so we've got very few events, just a few events at the top of stage 1 and top of stage 2. And then as we step down, we come down through the distribution of the seismicity. But this is actually a nice example to look at how fine the distribution is in stage 3. And the resolution we were expecting for stage 3 was around 40 feet. And that seems to be consistent with the actual spread of events that we see in the features here now. We step down. Oops, gone the wrong way. Okay, so this is coming down through stage 3, and then we'll see we get two different orientations starting to appear, and there's perhaps two parallel features here in the south as well. And this carries on, and that's around the open hole for stage 3. And here we're just above the perforation shot for stage 2. So you can see stage 2 is sort of started here at the perforation shot and grown in the sort of southwesterly direction. And as we come down, now we're in the zone of the open hole, and that's where I say we don't see very many events actually located on the open hole. And then on down through, and we come into this big zone of events here in stage 1. Okay. So quick overview now of what we've actually got to date. We have 820 events in stage 1, 957 in stage 2, and 1,431 in stage 3. The largest event we saw was in stage 3. Generally, stages 1 and 2 were smaller event magnitudes than stage 3. And the smallest events we've interpreted have been around about -2. And I'm just going to go now into some of the further processing we've applied to the stage 1 data, which will go on to actually apply to stages 2 and 3 in time. And this has primarily been clustering. And here we're looking to use cross correlation to identify groups of events that are very similar. And then we fit planes to the cluster. So the clustering is performed using specified trace windows about P&S picks to identify these groups of events. And if these groups of events, and we can find events that have got very similar waveforms, then we can interpret them as coming from the same patch of the feature that's generated them. You know, we in fact only use S-wave arrivals to perform the clustering because they basically got a lot better signal to noise, and so it's more reliable. So for the cluster, the setterings that we use, we find something we call seed events, and these are the events that are most similar to the other events. It's a bit of a tortuous description, but essentially the seed event correlates with as many events as possible at a correlation factor of greater than 0.95. And so once we find the seed events, which we could consider sort of master events, we then look for all the other events which correlate with the seed at a factor of greater than 0.8. And so those become the events that are in the cluster for that seed. The cluster windows themselves extend from -5 to 10 milliseconds about the S-pick. And this is to allow the correlation to move around and to allow for the slight differences in the picking when we've picked them individually, the events. So we use traces 2 and 3, these are the horizontal radial sensors of groups 6 and 7 to perform the clustering. So in fact, we're only using 4 traces. And then more than that, between traces 2 and 3, we search to identify the most distinctive waveform. So each cluster is actually only defined by 2 waveforms, and one from each of group 6 and 7. And we did this process for 2 settings of filtering. So we filtered for cluster set 1, as I've called it, where we just filtered a high pass of 10 Hertz. We didn't use a low pass filter. And then for set 2, we applied an 800 Hertz low pass filter. And the effect is that we get more events in the set 2 in fewer clusters. So here they are shown on the left is the set 1 clusters. And these are generally rather smaller clusters, more clusters, but fewer events in each cluster. And then on the right, the effect of the filtering is that we get more events in each cluster because the traces become more similar, and the clusters are larger in extent. But if we look at them vertically, in a vertical section, you can see still that even though the cluster 2 events, the clusters are larger, they are still distinctive features. It's just that when you look vertically down, you tend to get this effect of superposition of the dipping feature. So we've got particularly interesting in this set 2 is this feature down here at depth. So I think of these clusters as just representing very small patches on fault planes. So here's what I call an atypical set from a cluster from set 1, and it's just more interesting than the other clusters because it's got, let me describe it. So each of these traces are events, different events that are within this one cluster. All right, and so if you look here at the S-wave arrivals, you see how similar they are. So that's why they're all in the same cluster. But what I've done is aligned these traces to the P-wave pick, right? And so what you see is that all of these traces here on the left-hand side of the cluster all have similar P to S time. But this last three events in the cluster have got rather shorter P to S times, and that's because they correspond to these events that are a little bit shallower. And so the reason this is an interesting cluster is because it shows that all the clustering is doing is finding groups of events that have got similar waveforms. And generally they're on the same fault plane, but not necessarily. They can be similar if they're on nearby fault patches and they have similar sense of motion. So that's a typical or atypical cluster from set one. And this is one of the larger clusters. From set two, there are 38 events in this cluster. And you see here the great similarity of the shear wave arrivals. And that's why they're all in the same cluster. And that's this big group down here beneath the well. Okay, and then lastly on these clusters, these are what I call the seed traces. So this is for set one. We have 30 clusters. These are the seed traces. There's one for each cluster. And so each of these are different events. And you see very small changes here in the shear wave waveform. And so this is the unfiltered, this hasn't got the low pass filter applied to it. And so we see more distinctive features in the cluster. And then this is the other radial component. And so between these two components, it's able to identify these rather small clusters. So stage one, I just want to emphasize the clustering, it can't improve the azimuthal accuracy of the event locations. This is constrained still by the hodogram accuracy and appears to be around sort of plus minus 100 foot in the plan views. However, what the clustering does do is improve the relative accuracy of the depth and the offset of the events within each cluster by using cross correlation to pick the S-wave arrivals. And if you imagine, if we now apply this to our stages 2 and 3, where we've got the network type locations, then the clustering will also improve our accuracy in the horizontal direction. So here I've divided cluster 1 up into 3 stages just to have a last look at it. And so this I call P1 here, and 2 and 3. And so P1 is when the injection is increasing, P2 is when we're injecting at peak rate and then stepping down, and P3 is after we've shut in. And what we see then is the flow and pressure increasing. We see the seismicity developing above and below the well. And here, this is when we're actually at constant flow, or towards the end when we start to decrease the flow rates, and we see that the seismicity has gone up and across and back down again. And so following the shut-in, we actually see the events appear up here, you know, above where they were during the injection. Here's the B-value plots. And really interesting to say about this is that the B-value plot here in red for the clustered data from step 1 has a pretty similar value to the B-value shown in green, which is for all of the data from step 1. And so the clustering isn't is representing the distribution of events similarly to the whole data set. And the last thing about the clustering and the locations for stage 1 is just shown in this plot. And here the important thing is not really where the events are, but where they aren't. And what we can see, these groups of events here and here, is we've got the white space between them. So it appears that what we're looking at are fractures that are being activated, and we see the microseismicity, and then we're seeing aseismic zones between these features where presumably we have flow, but no seismicity. And here's the last little thing I want to show, which is the work of Demetrios, where he's been fitting planes to the clusters we got from stage 1. And so there are 30 planes shown here. And I'm going to zoom in on just this area here where there's the most dense seismicity and the most planes. Oh, this blue feature here is anomalous. and it's due to this single event up here causing the plane to be misfitted. So here we can see quite a number of small patches, as I think of them, where we've got clusters of events defining these small planes. And now if we rotate these events a little bit clockwise, what we see is that these patches all have similar orientations, and we've got daylight between them. So it's as though we are looking at fairly planar features on the fractures. So I hope I've pretty well done it in time. So next, what we have to do is to find some more automation for the travel time picking. And the preparation of these clusters for stage 1 has been a lot of work, and we have to make this more efficient. And then we'll apply that to cluster processing of stages 2 and 3 and follow it up with fitting planes as well. We also have one other task, which is to look at the accuracy of the holograms in stage 1. We want to get a better view on how accurate those event locations are. And because the geophone chain in 58 was in the same position for all 3 stages and was never moved, we can look at the azimuths for the events in stage 3, and we could compare the hologram azimuths with the event azimuths from the network locations. And in this way, we can assess which of the groups is perhaps more reliable for using in stage 1 to determine the azimuths. And that's all I have to say. Thank you very much.
Thanks, Ben. Questions? No one typed any in the chat. So if anyone wants to raise their hand or even come off mute, we have a moment or two. Go ahead, Colin.
Hi, this is Clay Jones. I have a question.
Go ahead,
It looked like the fractures in the open hole were emanating from where the check shot was fired. Is that where they were coming back in towards the well rather than at the end of the casing chute?
That's right, they were, but they were, the events occurred there before the check shot was fired, of course. So they're coming back in towards stage, where are we? Yeah, so they're coming back in here towards the perforation shot of stage 2, but the shot is not there. So I don't think they're being influenced by the perforation shot. That's what
I meant for the open hole perforation shot. For stimulation 1, it looked like the fractures sort of tied back into the well there.
No, they don't really. And yeah, so there they are. I don't know if this is a very good, where's the best place to see it? So here, yeah, they're sort of just scattered around the open hole. There's no distinctive feature of them coming into the perforation shot.
Okay.
Yeah.
Colin?
Oh, hi. Thanks for your presentation. So as we open and propagate fractures, then the velocity in the medium will change. So how are you accounting for those changes in velocity in locating the events?
I don't. And it's a good point, and I don't know how much it changes by and whether we should. I'm sort of encouraged that there's no obvious sort of shift going on. But yeah, we don't go back and re-perform the check shots into the perf, so we can't cross-check it really.
Yeah, so we know from the DFN work that this is a fractured medium, and so when we inject fluids at pressure, then we'll start opening these fractures and also propagating fractures. And so this will change the velocity of the medium. And of course, we can calculate that using effective medium theory. So it would be interesting to compute these changes in velocity and see how that affects the locations.
Yes, I agree. What I would say, just looking at these plots now, is that so this is the depth interval that contains the third perforation shot. So this interval contains the shot, and they're starting pretty much where the perforation is. So Yeah, so there we are above it, and there we are at the perforation shot. So my sense is that we're not far out, but it would be interesting to have some proper guide as to whether that's really reliable.
Thank you. Alita, I see you typed a question in the chat. I'll let you just ask it or make your comment.
Oh yeah, no, I was just saying that I would love to see the sort of fit planes orientations on a stereo net. I'm seeing a lot of those west dipping features that I was seeing just in the just microseismic locations, not doing the clustering. But I just wanted to see the distribution of those orientations.
Yeah, you're quite right. And I enjoyed your presentation actually a few weeks ago. So thank you for that. And the reason I didn't show this plot is because it's very tempting to be, it's very tempting because it actually shows the orientations that you probably like to have, and it agrees with the expected orientation. But I'm wary about it because we have this problem of azimuthal error in stage 1 because of using just the hodograms to locate it, and it would tend to agree anyway. So I'm being a bit cautious, and that's why I haven't displayed it.
So we're going to get some more plane fitting for the other 2-stage.
We will
data?
do, yeah.
Great.
We'll do it for the other 2 stages, and then I'll have more confidence about it.
Yeah, and I'd really like to stay in touch with you and Dimitros on the
question.
I'm sorry, Ben, I spoke over you, but I was saying I'd really like to make sure we stay in close contact as you work those clustering for stage 2 and 3. I'm really curious to see how it comes out with our initial interpretation of planes, and we could actually take whatever you come up with and also do a similar evaluation for some of the travel times and flow and transport that we're using. What we have. So I think it'd be great to do that early part of next year. So
well, yeah, just warn you, it is a lot of work, so it may not be as soon as you'd like. I'm sorry, but that's how it is.
You know what? I'd almost be thankful for that because if you get in right at the last minute before we start drilling, and I have to try to redo and scramble to redo all of our analysis to check it. So if you want to wait, take your time and do it late spring, I think that'll be fine. I don't think it's going to change much of our interpretation in the bigger sense. So it'll still be an interesting experiment to look at. So, well, if you don't mind, Ben, I'm going to transition here since it's about a little bit over half past the hour to Stuart. Stuart, if you're ready, you'd like to take over the screen.
Okay.
We're now working with stop something. No one news. Is that stopped it? Good.
Got it.
Okay, just double checking here that you can hear me, and
we got you, sir.
And you can see my screen in presentation mode.
You're good.
Okay. All right. All right. Good. Okay. So what I'm going to present to you right now is our provisional results of the analytical data that we obtained on samples of flowback waters taken in series during or after each of the 3 stimulations. So I'll just preface this by saying, and I'm not sure what Rob said to you last month, what we learned or what we received was entirely unexpected. As a geochemist who spent a lot of time looking at hydrothermal fluids, the compositions of hydrothermal fluids and a number of different active environments, and also around ancient environments of hydrothermal activity. The mineral mountains, which are here in the background, which is largely made up of granites and aluminosilicates, seem to be relatively benign solids in terms of what you might think would be able to release in a way of soluble elements. So what I'm going to show you is something that was entirely unexpected, and we're still working through in terms of the significance, and it might take a little while to get clarity, but it's pretty intriguing. And all of a sudden, There's some work for the geochemists who are interested in EGS. So, and for those of you with experience in unconventional oil and gas, you might see some similarities in terms of the compositions, and I'll be interested to hear from any of you with that background regarding what you're going to see in the following few slides. I just thank my colleagues here, Clay Jones and Pete Rose, for helping out with this presentation. Okay. All right, so just to refresh your memory, the stimulation program, there were 3 separate stimulations. Ben just talked about the seismicity, the microseismicity around these. Clay has compiled the results. This is from the report by Kevin England and John McLennan. So what we're seeing here is this is stimulation 1, stimulation 2, and stimulation 3. And what you're seeing over here on that y-axis is the total volume in barrels. And so again, you're getting percentages of the total returned fluid compared to the total injected. So the injected amount is up here in this box, and this is the total returned. And these purple-filled or magenta-filled squares represent sample points. And these samples were taken by Pete Rose. Oops, don't want to do that quite yet. Oh, yeah, uh-oh. Might have lost control here. What's happening? I can only go forward, I can't go backwards. Let's see. Previous. Okay, sorry for that. So these represent the points at which samples were taken, and you can see, at least in the first flowback, samples were taken throughout much of that period. In the second stage and in the third stage, most of the sampling is restricted to the earlier part. And you can see that about half of the total fluid injected was returned to the surface. So that's the stimulation program. This is the setup for sampling. Initially, there was a separator put on the surface in the event that there was any two-phase fluid flow. John tells me that he thinks that there might have been some in the early part of the flow back from the first stimulation, but I think from what my understanding, talking with John and Pete, was that the flows through the separator were somewhat feeble, and they resorted to just flowing back into the pit. And so you can see some splashing water here, and sampling was done from that location rather crudely, just by collecting water in a bucket and then transferring it to vessels for later analysis in laboratories. Our samples were sent off to the BYU laboratory, where a full suite of analytes were measured. They include typical major elements and species that are characteristic of geothermal fluids. And I'll work through those. I'll work through most of them, as well as some trace elements, and also deuterium and oxygen isotopes, or hydrogen and oxygen isotopes. And I'll show you the results from of many of these analytes. But first, let's just talk about the tracers just briefly. As mentioned, we do have tracer data. So Pete was out there, and he injected 3 distinct tracers for each stage. And in sum, what was observed was that each stage had its own distinctive tracer that came back. at no point were there any real significant contaminations from the previous stimulations. So stage 1, stage 2, this is a separate tracer, and you can see there's just a minor amount of the stage 1 tracer coming back. And then in stage 3, this is the stage 3 tracer. And again, you can see contamination from stages 1 and 2 showing up. And it wasn't until the bridge plugs were pulled that you can see increasing concentrations of those earlier tracers. The other thing contextually that's relevant is to understand what was injected. So the water that was pumped into the well during each of the stimulation was culinary water from Milford. So this is the Milford Golf Course, which is where the well is. And so there was, lubricants were added to reduce friction. So this typical slick water, and those treatments were applied in the first 2 stimulations. But then on the third one, the additives included a cross-linked polymer and also micropropant. And these have some effects which will be noticeable on the results that I'm going to present to you right now. So in the following, what I'm going to show you are time series plots of various elements. And you're going to see the changes that correlate with basically the proportion of water flowing back. And well, you'll be able to see for yourself, and I'll just dive straight into this. So the first element that we'll look at is chloride. So over on the y-axis, this is milligrams per kilogram or parts per million. And you can see the 3 different stimulations are represented in different colors. So this purple color represents stimulation 1, the orange stimulation 2, and green represents stimulation 3. And oh, isn't it striking? This transformation in terms of the composition is extraordinary. We're going from basically drinking water to something that you wouldn't touch. You wouldn't even give your worst enemy this to drink. This has become a non-potable water. It has become loaded with chloride, most notably, and also corresponding cations. So I'm not going to show you any other anions. Suffice it to say, the sulfate was consistently around 100 ppm, didn't show any noticeable changes, and we haven't analyzed bicarbonate yet. So you can see that stage 1 and stage 2. Also, we had an earlier sample down here, but the sample was compromised on shipping to the laboratory, so we didn't get an analytical result right at the start, even though the sample was taken. But you can see from stages 2 and 3 that the water being injected, or that was injected, was initially a very low salinity water. And so all of this change is a consequence of injection. And you can see that stimulations 1 and 2 closely correlate with one another. Whereas in stage 3, we get completely different response. And I think it's a pretty straightforward assessment that those cross-linked polymers are having some impact on whatever is making these elements available for dissolution and mobilization into the aqueous phase. So now I'll just show all the cations. So sodium in the upper left corner, and you can see pretty much a similar trend that parallels what I just showed you for chloride. Stimulations 1 and 2 show really dramatic increases in sodium concentration that parallel one another. You can see here in the stimulation 3, at least the early phases, it looks similar. And then by the time you're getting to an advanced stage of flow back, it's somewhat muted. I have to point out here as well that, so these flowback waters, this early water is basically water that's left in the drill pipe and hasn't touched the reservoir. It's only these later waters that are interacting with the reservoir. And so that is where this, where these elements are being acquired by the fluid phase. There's really no evidence that any of this is coming from the casing itself. So we interpret that all of this change that we're reporting is a consequence of some form of water rock interaction in the reservoir over really very short periods of time. So you can see a parallel trend in the potassium. Calcium is pretty similar. I would say if you look at stimulation 2, you're seeing not quite the same degree of response that you're seeing in the chloride or the sodium and potassium, but still it's similar. And then if we go over and look at magnesium, we're seeing a completely different response. So, and a response that is, of all the things that we might predict, is the one that could be, as well as explained, it can be explained by interaction and with, let's just say, clays, and that you would expect that on heating, magnesium would be titrated out of solution. So the magnesium in the drinking water from Milford is relatively high, and I say that from a geothermal perspective. And the flowback waters are significantly reduced in terms of their magnesium concentration. Just looking at these trends, this is the aggregate is what tells you that in addition to just knowing the configuration of the well and the casing volumes, et cetera, that calcium, sodium, and potassium are all increasing and magnesium is decreasing, tells you that there's got to be some sort of interaction in the reservoir. If we go on to what geochemists would normally refer to as neutral species, these are species that don't have an ionic form at the pHs that in the range that we expect. So silica, arsenic, and boron, they're all weak acids and they're not ionized. Silica is usually measured in geothermal fluids because it's a very good chemical geothermometer. And you can see the concentrations reach about 200 milligrams per kilogram maximum and then level out. So it's pretty consistent in most of the flowback samples that were analyzed. To give you a comparison, when we usually, so there's abundant quartz in the reservoir rock that would seem the most likely mineralogical control on silica. And these concentrations correspond with quartz silica equilibration temperature of about 180 degrees C. That's at 200 ppm silica. You might say, well, maybe that's not unrealistic given the reservoir temperature was 225, but if full equilibration had been reached, we would expect silica concentrations up at this level here. So you can see again that in stimulation 3, it seems that the additives had somehow impede the solubility of constituents. However, that's happening. So we're seeing a parallel effect as to what we've seen previously in the ions. So moving forward, so another parameter that's commonly used in geothermal geochemistry is the sodium-potassium ratio. It gives it's also used as a geothermometer. And I would just say that it looks like the flowback waters that have interacted with the reservoir, they all have similar ratios of around 5 to 6, and these would correspond to equilibration temperatures in the range of 275 to 300 degrees C. I wouldn't read too much into this right now. I'm just providing it for comparison. Probably I should just go back and note here that in the slides I've pointed out where the nearby Roosevelt Hot Springs range of compositions for components are. So this is sodium, calcium, magnesium. You can see the Roosevelt Hot Springs waters are very low magnesium waters. And then if I go back to the chloride, this is the range for chloride. One might think, oh gosh, look at that. These are all show some similarity with these natural hydrothermal fluids that are interacting with the same rocks in a convective heat transfer and classic hydrothermal regime. I'd be reluctant to jump to that conclusion, but the similarity is noticeable. So going on to some other weak acids, boric acid, usually just reported as boron, and we're now looking at micrograms per kilogram. So we've got much higher numbers here, but the range of values for the first 2 stimulations is on the order of 5 to 10 ppm. And again, you can see the close correlation between stimulations 1 and 2. And then in stimulation 3 now, boron jumps significantly, which suggests that there might be something in the additives that is being detected. And then if we go on to arsenic, arsenic is also a weak acid, and it is similar in its makeup, in its molecular makeup to both silica and boron. So this is arsenious acid. It is basically combining with hydroxyls. You can see that there is arsenic that's being dissolved and mobilized by the injected fluid. But you see that it really jumps in stimulation 3. And again, you'd have to infer that there's some additive, or so this is can be attributed to the additives used in that third injection. Okay, just doing some really crude interpretation here. The total mass mobilized in each one of these injections is striking. So if we take the concentrations and multiply it by the total amount of injected fluid, so we're getting 5 tons, 2 tons, and 1 ton in injections 1, 2, and 3, respectively. So there's been a significant amount of material, solid material that's been dissolved and returned to the surface by this stimulation program. The overarching question in all of this is like, what's happening and what's causing it? And just before I get to some speculations, there's one other bit of information that will be of interest to the geochemists, and that is the stable isotope data. So for those of you not familiar, stable isotopes of oxygen and hydrogen are represented in a plot that looks like this, where we're looking at relative change in the oxygen 18 versus 16 ratio. So that's plotted on the x-axis. And on the y-axis, we're looking at relative changes in the deuterium to hydrogen isotope ratio. And these relative changes are judged against a standard, and they're reported in a per mil sort of unit of concentration, if you like. Per mil is analogous to percent, but it's parts per thousand change, not parts per 100. You don't really need to get too bogged down into this sort of notation. What you really need to know is that the Milford Golf Course waters plot down here. So these are samples that were taken in 2015 and 2016. And then there are other waters that we know that occur naturally in the Mineral Mountains that plot on these crosses or plus signs. And collectively, these plot on something called the meteoric waterline, which is a representation worldwide of basically rain that falls out of the sky. We also have data from Roosevelt Hot Springs. It plots down in this range. These results plot down in this range right here. And the flowback waters are all represented up in this array through this part of the diagram. And it seems to closely correspond with the meteoric waterline. What you need to appreciate is, so the waters are going in at a composition somewhere around here. So this is the start, and they're finishing up over here. So this change is extraordinary. All of this stuff is extraordinary, but this kinds of changes in isotopic composition due to water rock interaction is unexpected for any of the minerals that we know to occur in the reservoir based on the characterizations that Clay has done so far and that have been returned to the surface. So we're seeing both a change in the hydrogen isotopes and the oxygen isotopes that are concurrent. And this is a puzzling result. I would say that, one thing, you might say, well, is it possible that there's some previously unidentified exotic water or native water in the reservoir that's somehow interacting with the injectate? And I guess that's possible, and that would be a simple way of accounting for this trend right here. It's got to be a pretty saline water, and it just seems surprising that we haven't seen it before in any of the other drilling. So the other possible effect that I'm going to suggest is that perhaps this is interaction with clays. Clay minerals are the only solid phases that we can anticipate that are going to have any significant amounts of hydrogen in the structure of the mineral. So you might see exchange of both oxygen and hydrogen simultaneously. For all the other phases that are in the reservoir, solid phases, they're aluminosilicates. They have abundant oxygen, but they do not have abundant hydrogen. There are some micaceous minerals, but it doesn't seem likely that they could account for this sort of extreme exchange over such a short period of time. Just want to point out that Clay has identified seams of clay on some of the fracture surfaces in the core. So this is an interlayered montmorillonite chlorite species that's been identified, and he's done quite a bit of characterization on this, and he describes it as a microbreccia. So it looks like it's a product of shearing, etc. But if clays are present on the surfaces of the stimulated fractures, then perhaps this is contributing to some of the effects that we're seeing in the compositional changes of the flowback waters. I would just say that I suspect, but it's really an early interpretation and subject to a lot more investigation, that most of the changes and transformations that we're seeing are due to surface reactions that are taking place during the stimulation. Further details about what those surface reactions involve, I think, is elusive, and there might be some people online who know better, have some suggestions, but I think in general, we're pretty surprised at these results and pretty intrigued. And I guess, I think I'll just leave it there and open it up to questions and see what sort of discussion ensues.
That was actually very informative. I'm almost a little bit of a panic trying to organize how to put all this together, Stuart, but very exciting. Ahmed, I see you had a question in the chat box. Do you want to ask it, and then we'll move on, open the floor.
You're not the only one panicking, Rob.
Who had a question? Sorry.
Oh, Ahmed,
Luke?
Murzug.
Who?
Oh, okay. I'll just read it. Wasn't the magnesium in the frac fluid because it was produced on high quantity, then got reduced? I think the well might first produce the fracking fluid before producing formation fluid.
Well, I don't think there's any formation. Personally, I'd be surprised if there's any formation fluid. I think most of us working on Utah Forge would be surprised if there's any native fluid at all. But maybe my colleagues could confess now if they think otherwise. That would be an interesting revelation. I think mostly what we're seeing are the effect of magnesium being titrated out of the injected fluid by some sort of water rock interaction. Details.
Oh, go ahead, Joe.
Yeah, I think given the permeabilities of 30 microdarcies or so, and the fact that we've drilled 6 wells with no fluid production, I think we can argue fairly strongly there is no fluid in those rocks.
Very well. I see everyone's questions. I will get to you. I'll just actually be patient until I call on you. Eric Sonnenthal, you made a comment or an observation. Would you like to share it?
Yeah, sure. I mean, it is pretty amazing data, Stuart. And it seems like the chloride, though, is kind of the key to it, because I know you're saying there's no fluid, but even at Newberry, we saw an increase in just from the pore fluids that are high brine, so high salinity. So yeah, I just don't understand how the chloride could get that high without having some kind of a brine, that's being contacted.
So and the only other thing is, which I failed to mention, but I was meant to, is if there was a salt formation down there that was, just loaded with halite, sylvite, and et cetera, and would be readily soluble. And of course, it might not even be recovered during drilling if it was present. So, but geologically, I think that would be another surprise. I think it's, this is the sort of stuff that causes cardiac arrest in geologists. We don't really anticipate, well, maybe not geologists, we get excited about this, but if you're thinking about,
Yeah, I just looked at the Salton Sea oxygen and hydrogen because I was kind of curious. And you see these similar kind of trends in the deep brines, and you do see a lot of carbonate down deep. So yeah, maybe there's something buried down there.
Well, that's always the fallback for a geologist who can't explain results, is that, yeah, we haven't encountered whatever it is that's causing the effects. But anyhow, well, there'll be a lot more discussion about this. Where, Eric, are the Newberry data public domain?
Yeah, I don't think we ever. It's definitely in the reports and then online on the geothermal data repository. So I mean, we didn't get huge, but we went from like 0 to 30 ppm chloride, which is nothing like what you saw.
Okay.
Certainly, we were picking up whatever minor pore fluid, but then we didn't have. Yeah, we're on a volcano, not sitting in a base, kind of a basin.
So we can't see any of these kinds of concentrations in any of the groundwaters in the Milford Valley. And if we do, we attribute them to outflow from Roosevelt Hot Springs, and we can trace that. So just for reference. Anyhow, other questions?
So I'm going to just transition to Alida, which was my cause of panic. And Alida, I'll let you ask your question yourself instead of reading it for you.
Yeah, I was astounded by those sort of just rough estimates of dissolved solids, just the volumes there.
Yeah, 5 times.
I kind of blew my mind there. I'm just wondering, have you tried to do any kind of back calculation of maybe some fracture area exposed, going from the volume to an area?
So could anybody tell me what the aperture of the fractures are during the simulation that took fluid?
We could bracket some uncertainty numbers for you. We'll go into that offline. But yeah.
Okay, but it's going to be sort of millimeter aperture, isn't it?
Or less.
Yeah. Yes. Yeah.
So I mean, it was literally I was fine tuning this presentation in minutes before I gave it. So it was the one thing I was thinking about, is trying to figure out what the fracture volume might, what the fracture surface area might look like. That's a worthwhile thing to do, and to constrain it by the microseismicity that's been detected.
Rob, can I make a comment, please?
Hold on, Luke is next, Nicole. Then we'll go. Then you're after Luke.
Okay, great.
Go ahead, Luke.
Sure. Can you hear me?
Yep.
So hopefully I'm not being too selfish here and trying to make my own life easier. But we're looking for a good water influent chemistry to do in our core flood experiments with the fracture flow studies. And we were thinking right now that we might use the golf course water chemistry, because our understanding was that a lot of the water during circulation is probably going to be sourced from there. Is that a correct assumption, or would you recommend some other chemistry for these experiments?
That would go to Joe, I think. Would be so. If you check the chat, Luke, I did provide some a link to where we actually went through and we provided the chemical analysis for a number of the waters there, groundwater, some local potable water, and also did some equilibration models to try to look at different temperatures and put it in the reservoir. So some of that has been done. You can look there. But Joe, where are we looking at now for our working fluid water for some of the flow-through experiments in the next test?
There are two options for short-term tests and low flow volumes. We'll look at the groundwater that was used in these tests. That would be the Milford City golf course water. I think long-term, we're planning to drill a water well on site, and the water from that has been described by Stuart, and it's the local groundwater. So I think both of those waters are viable. Again, groundwater from Milford City for short-term tests where we can work with a small number of frac tanks, and then long-term will be using the local groundwater beneath the site, and there are analyses for that.
Yep, and both those analyses are on that link I sent you, Luke.
Yeah, so you know, when I have 50 options to choose from, I just want to make sure that I'm choosing one that the team agrees with.
Basically, two.
Okay, so it sounds like you would concur with our current plan with the golf course water, or would you want us to test more than one influent?
Test two.
I would test two. I agree. Yes.
Test more than one. Okay, good to know.
And if you give me those results of that testing back in about 2 or 3 weeks, I'd really appreciate it when I start my reaction transport.
Oh, you know, doing tests over Christmas holiday is my favorite.
Yeah. Have no classes, you know, in this route. Get busy. Have fun, Luke. With that, I'll turn it over to Nicole.
Hey, Luke, the good news is that this transformation takes place over hours. So really, you're only restricted by your ability to set up the experiment.
Oh yeah, we're currently anticipating some pretty fast reactions, in part from learnings from like Tim Nisi and others. It seems like this stuff occurs very quickly. We'll see. It'll be fun.
We hear you, McCool.
Oh, okay. Very interesting data, Stuart. Very interesting data. I'll share with you some things that we learned in taking flowback water analyses from unconventionals. And what you see in some of these gas wells, not in oil wells, but in gas wells, is that when you flow the water back, you get salinities that are higher, much higher than the salinities of the formation brine or the injected brine. And the source of that high salinity and the high chlorides is evaporation of water caused by any phase change that occurs in the formation or in the wellbore. So we have a series of about 4 or 5 papers on this, of how, I'll sort of briefly summarize for you what happens in these gas wells. And maybe this is happening in these steam water type wells as well. We have not looked at that. But what happens is, if you look at Raoult's law is basically the mole fraction of water in the gas phase, which is the vapor pressure divided by the pressure. As the pressure decreases, the mole fraction of water in the gas phase increases. And that really causes evaporation, that causes salt precipitation occurring in parts of the wellbore and parts of the formation. And so you can have a source of salt that is completely related to the phase behavior of the fluids in the wellbore and in the rock. So just a possible explanation, I mean, I haven't thought this through, but almost definitely in gas wells and unconventionals, you see this effect very prominently. You see very high, in fact, you get saturated salt brine back in many of these wells as a result of this mechanism. So it's a mechanism that's worth exploring, and it might be something, and it happens very quickly. It doesn't require, it requires minutes or hours for this thing to actually happen. So maybe we can discuss it offline, but I wanted to propose that as a possible solution to this dilemma, which is a very interesting dilemma. I just don't see any geochemical explanation or in situ brine explanation. So I'm thinking of this as a possible way of explaining this.
It's a very good idea. Stuart?
McCool, thank you for that, because it was exactly what I said to John. I said, and John McLennan, and I don't have much oil and gas experience outside the first 9 months of my career when I worked as a mudlogger back in the 70s. But I am aware that in the unconventional flowbacks, just as you described, this incredible transformation in the water chemistry between injectate and flowback. And I've always been intrigued by it, and would be very interested in reading your papers on this subject. And I've heard the other oil and gas experts around EGI refer to this, but I've never felt like I got a very satisfactory explanation out of it. But I would be interested to learn more. And
let's talk offline. And this is a very different system than we have in unconventionals, of course, with steam. And
so it's hard to know where to see where there might be gas coming in. Like a free gas phase in the reservoir, but this might be something that would be.
It's the steam. It's not the gas. It's the steam. that you know, in a separate.
So at 7,000 psi, I don't think we're getting to two-phase conditions.
Well, but somewhere along the way you are. Somewhere along the way you are, right, as you drop the pressure. So there is phase transition that's happening in the wellbore.
Okay. Anyhow, just based on what, it has to be explored. I think we need to entertain the multiple working hypothesis and keep an open mind about this. And it's going to be difficult with the materials that we have to really come up with any. I mean, we might get some more permissive evidence, but until we do another stimulation, we're not going to be able to do get any more data. Clay can do more mineralogical assessments, but so another thing I would say is I'm going to bet this is a transient effect, and it's probably not sustained once we go into long-term circulation. But it could be very relevant because the Stanford group has a tool they're developing as part of their R&D support, which is using a selective ion probe that detects chloride. And the idea proposed by Roland is that they would see different concentrations of chloride at different feed points. And so seeing how much chloride is being mobilized, it may really be a tool for its time in the early circulation testing once 16B is completed. We'll see. But look, this conversation is just beginning. I think it's going to be a pretty vigorous discussion, and I would include all voices. I don't think anybody owns an advanced understanding of what's going on here.
Yeah, no, I agree. And so I think it's just another possible thing to explore. And
agreed. Yeah. I wasn't referring to you specifically, Mukul. I was actually just in general, but I think what we see from an unconventional experience has got to be a first step in sort of, because there's so much more measurement and data around these kind of transformations. So
it just struck me that this high salt concentration, the high chloride concentration that we see in unconventional gas wells is similar to what you're seeing here. And so there may be some commonality there. I don't know.
Yeah, I'll look forward to. Well, yeah, we can talk about it. But if you've got papers, please send them through.
I will do that.
Okay, thanks.
Thank you. So Ben made an interesting point in the discussion. Ben, why don't you share that with the group for us? It's actually really interesting.
So what I was just observing is that from the seismicity, it appears that stages 1 and 2 are interacting. And I'm no chemist, but I was just wondering if that maybe some part of the explanation of why at least you see similar geochemistry in stages 1 and 2 versus stage 3.
I trust you, Ben. I'll be looking at your data. I don't think the chemistry is diagnostic, but so there is another interesting thing here, and I think if I can, Mukul, if you're listening, so what do you think about the cross-linked polymers and how they might be interacting? Because would they suppress any of those interactions that you described in unconventional gas?
So, very much so. Yeah, the polymers and the cross-linkers and so on have a profound effect on the phase behavior and on the deposition of any of these precipitates.
Okay. So maybe Ben, if you could tell us that you can hear any cavitation or any kind of phase transformation rather than just snap, crackle, pop related to opening fractures, that would be a real breakthrough. So we would love to be hearing steam bubbles forming, nucleating.
Yeah, not just yet.
Well, Rob was planting some stretch goals, so it's
well played, Stuart. So I think this would be our last comment here, and Eric Sonnethal came back in. Eric, why don't you come back in and share that?
Yeah, it'd be interesting to see if you could do a selective leaching, or at Yucca Mountain, they did ultracentrifuge and they were able to get out pour water out of rocks that were pretty tight, you know, that you could never see water. So it'd be just interesting to see if you guys haven't looked at any leaching of any cores.
That's a good idea. We'll also be collecting, Eric, hot core from 17B, and you know that may be a place that we can do it before we see that evaporation. At least we'll collect core. It's a great idea.
All right. Thanks, Eric. Thanks, Joe. Thanks, Stuart and Ben. And I want to thank everyone who joined on the call. I can tell by the way the attendance stayed on through the entire time that the topics were very timely and interesting for the group. So I wish everyone happy holidays. Hopefully you all get to enjoy a little bit of time with family and friends over the next few weeks. And I wish you all the best of luck, best health, and we'll reconvene in January with some more exciting talks. So thanks all. This has been a great year. I really appreciate everyone.
Thank you all.
And I would, last shot here is if there is a topic you'd like discussed the next year, send me a note and I'll see if we can get it on the agenda. Or if you'd like to speak, same, let me know and we'll see what we can do. With that, we'll close. Thank you.
Thanks, Rob. Bye-bye.
Thank you.
Bye now.